Nature is nonlinear. Nature is mechanics. Nature is composite. Nature is structured. In short, nature is the dance of nonlinear mechanics, of composite structures. प्रकृति गैर रैखिक है, प्रकृति यांत्रिकी है, प्रकृति समग्र है, प्रकृति संरचित है. संक्षेप में प्रकृति समग्र संरचनाओं के गैर रैखिक यांत्रिकी का नृत्य है. भूमिमंगलम भूमिमंगलम उदकमंगलम उदकमंगलम अग्निमंगलम अग्निमंगलम वायुमंगलम वायुमंगलम गगनमंगलम गगनमंगलम सूर्यमंगलम सूर्यमंगलम चंद्रमंगलम चंद्रमंगलम जगतमंगलम जगतमंगलम जीवमंगलम जीवमंगलम देहमंगलम देहमंगलम मनोमंगलम मनोमंगलम आत्ममंगलम आत्ममंगलम भूमिमंगलम उदकमंगलम अग्निमंगलम वायुमंगलम गगनमंगलम सूर्यमंगलम चंद्रमंगलम जगतमंगलम जीवमंगलम देहमंगलम मनोमंगलम आत्ममंगलम सर्वमंगलम भवतु 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 सर्वमंगलम भवतु 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 सर्वमंगलम भवतु भवतु भवतु. ओम.
Okay, good morning everybody. Are you able to see my screen? Blackboard?
Yes, sir.
Okay, thank you. So we will conclude the bigger picture or the philosophical way of looking at our course so that we can then start fitting the details of it within this canvas, so to speak. So that's the whole idea. We're pretty much done with all the four words, main words there: nonlinear mechanics, composites, and structures. We are just left with the preposition of. So as we mentioned, it's basically A352 nonlinear, we already mentioned, is the ability to perceive reality. Okay. Even amidst or within a model. Okay, so that's essentially the ability to perceive reality within the model means that you should be able to create a very accurate model, and then from the model whatever you infer should be something that is really useful for your reality, or whatever is let's say the actual flying vehicle or an experiment that you're doing in the lab which you're modeling. You should have a good inference for that, and that is possible only with respect to the model being rigorous in a certain way, which means that the kind of assumptions you make in developing your model, etc., should be those that are acceptable in the sense that they are both necessary assumptions to make, and also those which are apt assumptions for the particular aspect of reality that you're trying to model. Only then the inferences that you get from the model would be suitable takeaways for the reality. So that's essentially what we saw about nonlinear. Then going with mechanics, so we saw that it's basically the ability to perceive a stationary principle even amidst or within the motion that is taking place. So that's essentially what we said about nonlinear mechanics. And this is basically an attribute of something that we are studying, and that something that we are studying is the object of our study. And what is that object of our study? It's basically the composite structures. Structures that we are trying to study. So there's a certain nonlinear basically refers to a mathematical way of looking at it. Mechanics refers to a physics way of looking at it. So there's a maths and physics attribute of a particular actual physical entity, which is your composite structure. So just like for mechanics, nonlinear is an adjective. Similarly, for structures, your composite is an adjective, which describes the kind of structures that you're looking at. And the beauty of looking at a composite structure is that you can treat homogeneous or isotropic structures as special cases of the non-homogeneous or heterogeneous and anisotropic properties of the composite structure. So essentially you're looking at a really big superset over there in terms of the object, and it's essentially we are trying to connect that. And what is composite? We already saw it's the ability to perceive unity in diversity. And finally, we saw that the structure is nothing but our ability to perceive order even amidst chaos or within chaos. So this is the bigger picture that you need to be aware of, this being a 300 level course, and most of you being PhD students. So the final degree that you're getting is a doctor in philosophy, which means that the philosophical understanding of the depth of whatever you are knowledgeable in is very significant, and that's why world over this particular degree is doctoral degree is typically called a PhD, not a doctor in science or doctor in something like that, but it's basically a doctor of philosophy in science or engineering or arts or whatever the field might be. But essentially it's a philosophical degree that you're looking at. And if you look at the 100 or 1 level courses, they are typically like undergraduate level. The 200 level courses are typically your master's level, and 300 level courses are essentially your PhD level. And as I said, this is the only 300 level course that is being offered by the aerospace department in this particular semester, and so we are really lucky to be a part of that, because we are trying to get the bigger picture of what we are going to do. And especially those of you who are first semester students or first year students, you would see that there's a huge benefit in understanding the bigger picture before you get into the other courses, so that you have the where in that let's say a million piece jigsaw puzzle, each one of your small pieces that you're going to study in the other courses are going to actually fit in. So that way you're not kind of lost in the details, so to speak. You are aware of where those details go. There's always an argument between the utility of the breadth as opposed to the depth. And in many situations, and subjects, be it in engineering or science, these different branches of engineering have been partitioned so much, and each branch has been dug so deeply that most PhDs have been in that depth. But the trend for PhDs, especially in engineering lately, engineering in general and aerospace in particular, has been in multidisciplinary work, because that's where for a long time we were not capable of handling multidisciplinary work. One, because the individual aspects were not understood well, and secondly, putting them all together computationally meant something which is a very massive requirement, both from the hardware and the software perspective, which we didn't have at that point of time. Even if it was an experimental kind of a study, the kind of infrastructure that you needed to develop for a multidisciplinary study, even like, let's say, as simple as aeroelasticity, couldn't be achieved for a long period of time. And now we are looking at aero, thermo, servo elasticity and things like that. We are combining the various subsystems, because each of these subsystems in reality is nonlinear, just like what we are looking at here is the nonlinearity in the mechanics of composite structures. Similarly, the propulsion, there are certain nonlinearities. In the aerodynamics, there are certain nonlinearities. In the control law, there are certain nonlinearities. And when you all put them all together into a single system that is a flight vehicle, be it an aircraft, helicopter, launch vehicle, missile, or satellite, you see that the principle of superposition, as you very rightly pointed out, some of you, will not be valid, because each one of these subsystems is nonlinear, and when you're combining into a, let's say, a single vehicle, then you're going to have to deal with all of them upfront. In other words, you can't solve the structures problem separately and the aerodynamics problem separately and then try to stitch them together for the aeroelasticity. It will not work unless and until each one of those problems was linear. Then you could do something like that. But now you have a situation where the aerodynamics is also nonlinear and the structural behavior is also nonlinear. And if you want to really understand this well, you have to do the nonlinear aeroelasticity right from the beginning. So that's the essence of what we are trying to pinpoint over here in terms of the importance of the bigger picture as well as the importance of nonlinearities over here. So then we essentially saw that each one of these had a certain relevance in terms of the kind of capabilities that we as a structural engineer or as a structural designer needs to develop in order to accomplish this. The one with respect to the reality and the model was what we called as devotion. And the one with respect to the motion being the stationary principle is what we called as the discipline. And the one to see, the ability to see unity in diversity is basically your knowledge. And finally, the ability to see order in chaos is basically the action. So in other words, what are you going to do about the whole thing? So basically you're either analyzing or building the structures. That is where you're essentially seeing that. So these become the four pillars. The first one being devoted to the task that you have at hand, which is to develop a reliable model, that is, and to get inferences after you run the model. What are the inferences you get for the real structure is what that devotion is all about, getting totally involved without getting entangled into the system. So that is essentially the first pillar. The second pillar is basically your discipline in modeling your motion using stationary principles like Lagrangian, Hamiltonian, etc., wherein you try to minimize the assumptions that are involved. So typically what most people do, especially in the undergrad level or in very basic analysis, is to use a Newtonian mechanics rather than a stationary principle, and the kind of the boundary conditions, the governing differential equations that are obtained and solved, typically the kind of assumptions which are made are many a times lacking in rigor, and therefore you would see that they are prone to much more error. That is one reason, because of the assumptions. The second reason is that the Newtonian or way of doing the classical mechanics or continuum mechanics always involves lots of vectors, and when you have vectors, you are dealing with more complicated structures, complicated mathematical structural elements, which are having both magnitude and direction. Then you go to DADs or higher order tensors, you have much more in terms of the characteristic of each variable, and the ability to perform these calculations is to a limited few, and therefore you get prone to error. Whereas in stationary principle, almost always you're dealing with scalar quantities like energy, and therefore you have the accuracy that you can have is much more. First of all, the physics is much more accurate in the stationary principle, and then the derivation involves only scalar quantities and therefore is less prone to error. So that is the discipline that you have in terms of taking motion towards the stationary principle. And the third pillar that we build our entire course on, and its application later on in your careers, is on the knowledge. So the knowledge base is very, very critically important there. And when it combines with the other three pillars, which are like quarters, these four quarters become a single whole, and that is essentially the building that you build out of these pillars. So the knowledge that you understand, not looking at the composite as individual fibers and matrices, but as equivalently homogenized structure, gives you that ability to do that. So that's essentially the third pillar of knowledge. And finally, you have the fourth pillar of action. So if you have all the devotion towards your task, you're disciplined to do the task, and you have the knowledge to do the task, but you're too lazy to do the task, then nothing is going to get achieved. So to get out of your comfort zone and to act and to do your work is essentially that action, the principle of action. So it's only when you're devoted, disciplined, have the knowledge, build up your capabilities through your coursework, through your reading, self-study of journal articles, and these days watching videos, probably relevant videos, and then building your knowledge, and eventually using that devotion, discipline, and knowledge in actually doing an analysis or design is essentially your action. And so that's the fourth and important pillar. Now we are trying to combine this. As I said, nonlinearity is essentially to deal with mathematics. The mechanics is essentially to deal with the science, and the composite structure is basically what you're having as the real entity, a particular component which goes into the aircraft structure. And so that's essentially your an adjective over here, and this is the object, which is a noun. And so this particular object, you're looking at a certain mathematical and scientific aspect to that. And so that connecting entity is what we call as the preposition. And that's the only thing that we had not looked at in the last class. And that's basically off. So this preposition is basically telling that this attribute of nonlinear mechanics is associated with a particular object, and that object of interest over here is the composite structure. So that connecting entity is what basically takes us from what is essentially the motion's kinetic energy to the motion's potential energy. So the reason why kinetic energy is something that is considered to be a part of, you will see when we start applying the variational asymptotic method. So when we apply the variational asymptotic method, you will see the details of it later, but essentially what we are trying to do is instead of solving the problem in an exact sense, you're trying to solve it in an asymptotically correct sense. In other words, you're at first trying to solve with only the leading order terms in the energy, and then you slowly add on the higher order terms. So the first solution that you get, there's something called the phantom step, which we'll not worry about right now, but the first useful usable takeaway that you can get as a solution after applying the variational asymptotic method will be what is known as the zeroth order approximation. And you will see that whether it's the zeroth order approximation or even the first and second order approximation in most cases, the kinetic energy doesn't come into picture at all, even if you're dealing with fairly high speed dynamic problems. So that's essentially what it basically means over here, is that the potential energy is far more important, far more significant. Leave alone in continuum mechanics. If you look at mechanics as a branch as a whole, if you look at even the very popular Einstein formula, E is equal to mc squared. So what is essentially saying is that the amplification factor of c squared that you have over there is so large that the energy contained even within a static mass of small m, it could be a few milligrams or even nanograms, but because it is getting multiplied by c squared, and c is 3 into 10 power 8 meter per second, and it's squared, you see the amplification factor in terms of how much of energy it holds, and that's essentially your potential energy. So the potential energy, or what we will see in structures as the strain energy, plays a very critical role in terms of being the leading order term. And that's why you would see that all the terms related to the actual motion, the dynamics, drop out in the leading order terms, and you would essentially be solving the entire problem with just the strain energy alone. And no wonder you are talking of the principle of minimum potential energy and other things in your undergrad, but which were very useful because of this particular reason. But the reason was never told to you, that the kinetic energy is a very minuscule part of the overall energy, which is predominantly the potential energy, and a small part of it goes there. Even if you look at, let's say, quantum mechanics, and you're looking, we talked of relativistic mechanics is equal to mc squared. Leave that alone. Even if you talk of the quantum mechanics, and you see that within an atom, if you take the kind of kinetic energy that is there, is primarily because of the electrons, whose mass is very small or negligible compared to the nucleus, which consists of the protons and the neutrons, and that is essentially containing the potential energy over there. And that potential energy is far, far more compared to the kinetic energy associated with the electrons. And that's why you have the atomic bomb having so much of power, even in small quantities of the nuclear material that you might have. So because essentially it is tapping into that nucleus. And that is as far as fission is concerned. Fusion is an even bigger demonstration of the fact, like what is happening in the sun, the way it produces the solar energy, be it the heat or the light that we experience on Earth. The massive amount of energy is basically the nuclear fusion that is happening in the sun, in terms of hydrogen nuclei getting together to form helium, etc. So that fact is what this off basically helps us, which is why this particular attribute that we are talking about, namely the nonlinear mechanics is so very important for this particular object of the composite structures, is because this off is dealing with certain energies, and in particular it is the ability to perceive potential energy even within the small kinetic energy that is associated with the motion. So that is essentially what it is. And if you look at it from a bigger picture, or a more philosophical picture, essentially what you're doing is that it's from the potential energy that you're taking a small part out and making it into the kinetic energy. In other words, the potential energy is pretty much like what you would refer to as the creator, or its creativity. A part of that creator or the creativity essentially becomes that what you call as the creation. And here we are not talking of some creator sitting somewhere far away from Earth and dictating what is happening to us. I am the creator, you are the creator, we are all the creators. So essentially we are creating entities, especially as engineers. We have created so many synthetic structures which have been of great utility to humanity. So in that sense, we are essentially creating, but if you look at the basic aspect of what is actually happening there, it is is the potential energy from which a little bit of the kinetic energy is taken out, and that manifests itself. So the potential energy is actually existence, it's the reality, and then the model or the what you take out and create out of it is the kinetic energy, and that is essentially your creation. So essentially what we are trying to do is that we are it's the ability to perceive potential energy in the kinetic energy, because that's where it came from, and essentially the ability to perceive the creator and his or her or its creativity in the creation that we have made. So if I'm the designer of this beluga, so I have as a team created this entire aircraft, and this is my creation. I am the creator, and using my creativity I have created this aircraft. My ability as a lead engineer should be to see myself and my creativity within this even before it is created. And once it is created, then you have that oneness with it which you can relate to, and therefore first of all you have created a masterpiece which can be really useful in whatever applications it was designed for. And then if it has any issues going forward, you will be able to address those issues quickly and effectively. So that is the essential attribute of a good engineer, to be able to relate in such a way that's fully involved with this design or analysis or whatever we are doing, getting completely involved with the task, but without getting entangled in it. Because if we get entangled, then there is a little bit of subjectivity. They say even if a surgeon, leading surgeon, were to perform surgery on his or her child, then the hands could shiver. So typically even lead surgeons do not do the surgery on their own children. They let other surgeons do that, even though those surgeons might be less experienced and less proficient than themselves, because of that kind of entanglement that they have. So this is a very tricky thing, and it's a talent that we engineers should develop, that we get involved in whatever tasks we are doing, whether it is modeling tasks, whether it is fabrication tasks, manufacturing tasks, or analysis tasks, etc. Whatever task we are doing, get involved in it, but at the same time don't get entangled in it. So that is the it's the art of engineering. Most often we are taught in schools, engineering schools, the science of engineering or the maths of engineering, but equally important compared to these two is the art of engineering. So the art of engineering, in fact, for a long time, people used to talk about STEM as a very important area, especially in the US. People keep saying that there's not much interest in STEM of the American citizens, and therefore they typically get Asians like Indians, Chinese, Japanese, and Korean students are the ones who are doing PhDs in most of the engineering disciplines in the US universities, at least the top universities. So the reason is that they have not given enough importance to STEM, where STEM, where S stands for science, T for technology, E for engineering, and M for math. But I feel that you have left out a very important component there, which is which can make STEM into STEAM. So instead of dealing with STEM, which is your science, technology, engineering, and mathematics, you have to have what is called a STEAM, where you bring in the arts aspect to it as well, because there's a lot of artistry, and this is even more special for our course, the variational asymptotic method. It's not just me. You can ask some of the your classmates as well, like Renuka or Khwaja, who's your teaching assistant. Some of these people who have actually applied the variational asymptotic method to various problems, and you would see that they have seen a certain artistry in doing that as well. So that art aspect of it is very, very important, and that's where you are essentially seeing that creativity within your creation, and therefore you're getting involved without getting entangled. So this is a very important point. And if you look at it, essentially what that creator or creativity is, that's essentially or the potential energy for that matter, which is basically essentially the latent like you know that, for example, there is a latent heat in materials, and it gets removed or added upon depending upon phase changes that are happening, like when say ice turns into water and water turns into water vapor. At that transition point at 1 atmosphere, it typically happens at 0 degrees centigrade between ice and water, and 100 degrees centigrade between water and steam. So essentially what is getting released or added upon in those phase transformations is your latent heat, and that latent heat is also kind of a potential energy. In structures, we'll be dealing with it predominantly as the strain energy that is associated with the various components making up the composite structure. So you have a semi-monocoque construction of a wing, you have the skin, you have the spars, you have the ribs, and you have the stringers. So each one of them stores a certain amount of strain energy. So the overall wing stores a certain amount of strain energy, which is the addition of all of these. And within each one of those components, that says the spar, the flange, and the web, the two flanges, flange on the top, flange on the bottom, and the web have different amounts of energy. So that's the sum of that energy is energy of the spar. That is the strain energy stored in it. And within the flange, there are multiple layers in that composite laminate that you have, and each layer has a certain amount of strain energy that it stores. And within a single layer, there are fibers and matrices. So the fiber and the matrix and various other additives store certain energy within themselves. So you're basically building up that energy to create this whole structure that you witness as an aircraft wing, and then the aircraft itself to make it accomplish the missions that it was designed for. So essentially what you're having in terms of the actual vehicle, be it a flying vehicle or a vehicle which is going on water surfaces or within the water like a ship or a submarine, or you are looking at those which are going on the surface of the earth, like on a road, like your automobiles, be it public transport or a private transport, four-wheeler, two-wheeler, whatever, or even on tracks like the railways. Essentially what you're trying to accomplish is to move a certain payload from point A to point B and maybe back. So that's the motion that you're trying to do. But where is that kinetic energy for the motion actually coming from? It's basically the burn of the fuel that you accomplish. And that where is that fuel creating that energy from through the combustion process? It is basically the heat which is contained within it. And that's what you would have studied, especially those of you doing your MTech in your mechanics and thermodynamics of propulsion in the previous semester. So essentially you're looking at how that heat which is there within that fuel is extracted for a useful purpose, which is to provide the kinetic energy for this motion to happen. So that is basically again a form of a potential energy that is stored in the fuel. For potential energy in the sun that we discussed, the potential energy in a structure in the form of strain energy, all of these is giving lead to a certain bit of the kinetic energy, which is what we visually manifest as, let's say, motion of the vehicle, or let's say the deformation of the vehicle, or we are looking at it in terms of, in the case of a failure, the fracture that is happening in a particular material between between an interface of two surfaces, or a fiber breaking, etc. So various things that are happening, or all these motions are manifestations of that existence, that is the strain energy or the potential energy. So that's the importance and relevance of the strain energy or potential energy. We can't underrate it at all. So this is very, very important for us to understand from that perspective. So in that sense, you see the words that are used for the potential energy. Potential. Even when we talk of a human being, especially a student or a child, we say they have enormous potential. That means that, or an early career engineer, we say this engineer is highly potent, in the sense that he or she, through his career, can perform very useful tasks, engineering tasks. So that's basically the potential, which means that you're perceiving, even before the person does some work, you're seeing certain capabilities in them. That capability or is potential is actually hidden, but as a leader, as a recruiter, or as a human resource person, you're able to see that quality in that particular person, and therefore identify this person is suitable for this task, and put him or her there, so that the task is achieved appropriately. So in other words, that capability or is actually latent, just like latent heat. It is a hidden entity that only an appropriate seer or a leader can actually look at and perceive a priori, and therefore tap into that potential. Same way, the kinetic energy is tapping into the potential energy. And if you look at it in the bigger picture from a philosophical perspective, that potential energy is nothing but your death. Whereas your kinetic energy is life. This might seem very shocking to a lot of people, but if you look at whether it is kinetic energy or creation, it's just a small thing which is happening for a very small duration, we could say even fleeting, compared to for how long this whole potency has been, in terms of how long we've all been dead and how long we'll all be dead, compared to how long we actually live. It's a very, very, very minuscule percentage of the entire time. It's just a fleeting happening. It happens and then it disappears. But that small duration, we are actually enlarging with a magnifying glass and making it so important, because while it lasts, that is very important. Life is very important as it lasts. Motion is very important as it lasts. The creation is very important as it lasts. The model is very important as it lasts. The diversity is important as long as it lasts. The chaos is important as long as it lasts. But then we should never forget that the chaos was really order, the diversity was really unity, that the motion was really the stationary principle, the model was really the reality. It's just that it's kind of a game. You're playing a game by creating out of the reality of this particular structure. You're creating a model for it, and so that you can play around with the model. You can't play around with the real thing, so you play around with the model, and then whatever you learn from that game, you basically incorporate it in your reality. So that is essentially what is happening over here. And in that sense, the potential energy is akin to death, which is just another side of the same coin that life is. And out of that death, we are extracting life for a while and putting back the life back into it as the creators or the engineers who design and build various components and structures and vehicles out of this whole thing. And out of the vehicles, the system itself, like the airlines and the entire ecosystem of the aerospace, or the humanity as a whole. So that's essentially what is happening. So if you look at it, it's all coming from the same pool. That is one single pool that you can call as death philosophically, that you can call as potential energy scientifically, or in an engineering sense. And religious people would call it as a creator. Artistic people would call it as creativity. These are all just different words for the same thing. But essentially what you're doing is, that's one single entity or a bank from which you are withdrawing a little bit of the resource. Just like when you go to a bank, you have a big deposit, but you take only what is essential for your expenses. That is basically your kinetic energy. So the potential energy is what is your bank balance. Some people, of course, early career or students, we have a very small bank balance, which means that the potential energy needs to be developed. So how do you develop that potential energy is essentially what the purpose of life and death is. So that's essentially what you're trying to do. So this whole thing is that deposit, what you have is essentially non-dual. So in other words, the potential energy, death, creator or creativity that you're talking about, which is the ability to perceive that quantity is nothing but your non-duality. So in other words, you're not looking at even two quantities, leave alone multiple quantities. You're looking at everything as one latent entity from which everything else is sourced out in various forms, in manifestations. So whatever you manifest, you are actually experiencing, whereas what it really is existence. So you understand this essential difference between existence, which is your potential energy or strain energy for a structural engineer, and then what you're taking out of it to have a certain motion in place, that is essentially your kinetic energy, which is nothing but a particular manifestation or an experience. So this difference between existence and experience is very important to understand in this perspective. So what is this preposition that is there over here, which is of, oops. What is this preposition doing? It's our ability to perceive that non-duality even amidst or within duality. Or more appropriately, plurality. So the one becomes many because the one is boring. The one by itself, the creator and the creativity by itself, the potential energy by itself, latent energy by itself, strain energy by itself, death by itself is too boring. It lasts for very long, but you get bored. So once in a while you want to play this game as a leela, as you sport, and that sport that you exhibit is basically that plurality. So the one becoming the many in order to perform kind of nice drama which you enjoy, which you get entertained by, and you then put it back to where it originally came from. So that's essentially what you're trying to do in off. It's the ability to perceive non-duality even amidst plurality or duality. So that's essentially what you're trying to do. And here, just like we saw the four columns that were there to make this building were devotion, discipline, knowledge, and action. Now is the time that you're combining those with the help of what you have as a preposition of over here. And that combination is what you see in this perception of potential energy as kinetic energy, non-duality as plurality as non-duality, creation as the creator or creativity. And in doing so, you have combined these four columns of devotion, discipline, knowledge, and action into a single column of what we call as the integration. So just like the first one of perceiving reality in the model is Bhakti Yoga, the ability to perceive the stationary principle within the motion is nothing but your Raja Yoga, and the ability to perceive unity in diversity is your Jnana Yoga, and the ability to perceive order in chaos is your Karma Yoga. So for the Karma Yoga, you're using your body, your physical abilities, and then for the Jnana Yoga, which is to perceive unity in diversity, you are using your intellect. So it's an intellectual process as opposed to a physical process. So this is essentially a physical process. So these are all the processes. This is an intellectual process. And then you have essentially what this is an emotional process. And this is an energetic process. So there are various aspects to ourselves as well as the entity that we are creating, the flying entity that we are creating. There's a certain physical attribute to it. There's a certain intellectual attribute to it, especially these days with artificial intelligence being a very important part of most developments. But even before that, in terms of the control hardware, how the sensor data, because there are literally lakhs of sensors that are there on a typical aircraft, and each one of those sensors are getting certain data from the environment and from the structure itself and various other subsystems and subsystems that are there on the aircraft. But what you do with all that data, you have to process that. That is basically the intellectual happening that is there, and then you basically deliver that in terms of whatever the tasks are going to be. So that's important that you see that there are these four aspects to all of individuals, and the word individual itself is in the sense that it is derived from the root word indivisible. That means we are a single entity, and that's essentially the non-duality that we are talking about, and that single individual or indivisible entity from which we are looking at its various aspects, the physical aspect, the intellectual aspect, the emotional aspect, and the energetic aspect. And it's only when you combine the body, the mind, the intellect, and the energy, you are able to accomplish something that is of significance, not only to you, but to the society at large. So that's essentially what we are trying to do over here. So this is the ability to perceive reality in the model is your Bhakti Yoga. The ability to perceive stationary principle in motion is your Raja Yoga. The ability to perceive unity in diversity is your Jnana Yoga. Ability to perceive order in chaos is your Karma Yoga. And when you combine all of these, that is, you combine devotion, discipline, knowledge, and action, is what you get this integration, or what is called as the integral yoga, which a more beautiful word for it is Sankhya Yoga. The reason I say it's more beautiful word is that there is always a correlation between the name and the form. So there's a certain name associated with something, and then there is a form associated. If I say, let's say Dhruv, those of you with a religious background might think that Dhruv is a particular character in mythology, etc. But for those of us who are in aerospace engineering, as soon as we say Dhruv, especially in the Indian aerospace sector, we easily recognize that to be the Advanced Light Helicopter. So the name has a certain association with a particular form. As in other words, the word and its meaning are associated with each other. Now, how the word is associated with the meaning, how closely is it associated? If it's an exact association, just like when you have a set of complicated equations to solve, in some very rare cases, you might get what is called as an exact solution. Even in elasticity, we have the theory of elasticity. We talk about exact solutions to certain problems, which might be of very regular geometries, and the kind of boundary conditions and load distributions are such that you are able to get an exact solution even to those complicated set of equations, governing equations, essentially a boundary value problem or an initial value problem that you're solving to get an exact solution. So, if you're looking at it from a linguistic perspective, all that is there are certain quantities which have a name, which is essentially nothing but a word or a sound on the one hand, and it's basically the form of that, which is what you have, or the meaning that you give to that word, sound, etc. Now, if there is an exact solution, that is typically what was derived as the most ancient language, which even the American historian Will Durant calls as the mother of all languages, is Sanskrit. So Sanskrit is a language which has is like an exact solution for the meaning in terms of the word. So that's essentially what is happening. And then, as you shall see in the variational asymptotic method, many situations it's not possible to get the exact solution. What is the next best thing we can get? We can get asymptotically correct solution. solutions. That is, we can go as close to the exact solution as possible. So that's basically most of the Indian languages. If you look at almost all the Indian languages, they're all derivatives of Sanskrit, and essentially you are approaching that Sanskrit in an asymptotically correct fashion. So every step you take, you're getting closer and closer to that. And I know there are a few Tamilians also in the group. There's always a conflict between Tamil and Sanskrit. I do not want to make this a controversy over here. But Tamil, if you look at it, even in terms of the alphabet that it has, k, k, g, g is just a single letter, ch, ch, j, j is a single letter, etc. So it's a much more rudimentary in the sense that it's much more fundamental language. Rudimentary might sound demeaning, but fundamental. And that's where I talked about the phantom step in the variational asymptotic method. The phantom step is the one which extracts the most significant degrees of freedom of the system. So you have an infinite degree of freedom system in reality, because we're talking of continuous structures, and that's if you are able to solve for everything simultaneously analytically, you are getting an exact solution which is like Sanskrit. But if you're getting the main degrees of freedom which through which everything else can be described, then you're basically dealing with what is called the phantom step, which is akin to Tamil. So Tamil is like the phantom step, or what you extract as the most significant thing, because k, k, g, g, if you actually see how the sound, the signs of how these sounds are produced in your mouth, they're all the back of your tongue touching the top of your mouth, and then ch, ch, j, j is somewhere in between. T, t, d, d is the tip of the tongue touching that front portion of the top palate of the mouth, and th, 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 you're basically touching the teeth, and p, f, b, b, the labials where the lips are involved. So essentially each set of those is coming out one by one, whereas Tamil has only one letter for each one of these. So essentially that's like your phantom step. You will see when we apply the variational asymptotic method, we do not make assumptions like other methodologies, the way they typically approach the problem. If something is unknown, we are brave enough and courageous enough, those of us apply the variational asymptotic method, to say, yes, I do not know. Whereas most others, what they will do is make assumptions about it. They don't know the displacement field. They want to actually calculate the displacement field. That is the purpose of the whole thing. But then they will assume the displacement field is a particular linear function or constant or quadratic, higher orders like cubic, whatever. But they will assume a certain form to it a priori. So that means that you're getting into a belief system, you're getting into a myth. Whereas the variational asymptotic method is a courageous way of doing it, where we say that, no, I don't know this quantity, this is what I have to determine. I will get it from its first or fundamental principles. And when you're trying to do that, in many cases, it's not possible to do analytically in a closed form solution to get the exact solution. And that's where the asymptotics of the variational asymptotic method comes in, and you say, okay, fine, I can't reach the exact solution as it is, but I'm only an engineer, not a scientist. I'm not interested always in getting the exact solution. If it comes within an error of, let's say, 0.1%, 0.01% of the quantities that I'm interested in, that's more than good enough for me. It works. So how do I approach that? And how do I approach that for a large class of problems? That's where the variational asymptotic method comes in, and you start with the so-called phantom step, which is not essential most of the time, because it's already been done for typical beam problems or shell problems. So you have a jump start. You start with what has already been derived by the others. See, even when you're deriving anything from the first principles or from the scratch, as they say, you're not actually doing anything really fundamental. There is a huge body of knowledge that has already been developed in any field that you work on, and that's the reason why in any paper that you write, you give so many papers as references from which you got the information before you started off. So there's nothing that you can do out of nothing. So there is a certain level from which you start, and then which means that you trust those literature, and based on that literature you're trying to incrementally improve that body of knowledge to make it even more useful, better. It could be faster, or it could be more affordable, whatever you're trying to do, or a combination of all of these. But essentially that's what you're trying to do. You're taking a certain body of knowledge. Similarly, the phantom step for beams and shells has already been developed, so we take that and then go ahead and build. Similarly, your Tamil is a language where it's like a phantom step, where the minimum required number of alphabet is there, and then you build up on that, and eventually you reach the exact solution of Sanskrit, and everything else is in between there, especially the Indian languages. And the way I perceive, or even Will Durant perceives the non-Indian languages, is typically in the sense that they have made those assumptions. Like, we do not make assumptions in approaching the exact solution asymptotically, because we let the mathematics and physics themselves do it, rather than we intervening and say, no, this is big, this is small, I will assume this form for the displacement. Some people say, okay, I will not assume anything about the displacement, and seem as if they are doing the right thing, but they might be assuming, instead of assuming about the displacement, they might be assuming something about the stress, which is an equally unknown quantity, and therefore making an assumption either about the displacement or about the stress is equally erroneous, because that's a quantity that you're supposed to determine, and if you make already an assumption about that, you're influencing that whole process, and therefore you end up with a solution which is not going to be of much significance. So that is essentially what this whole process is, and that's why this integral or Sankhya Yoga is so important, where you're trying to combine the attributes of all of these four pillars of devotion, discipline, knowledge, and action in accomplishing what you're trying to accomplish in the variational asymptotic method, starting with the phantom step and then going to the zeroth order approximation. The phantom step by itself will not be something that you can directly apply, so you need to go at least to the zeroth order approximation, which is the next higher level. And then once you have the zeroth order approximation, if you want to do some accident investigation, failure investigation, or detailed design optimization, etc., then you have to go for higher order approximation, like a first or second order approximation, which is more than sufficient for most practical purposes. It's purely out of scientific interest. You can look at even higher order approximations if you want to. And this is only essential in that large class of problems where exact solutions are not possible. If exact solutions are possible, you might as well go ahead and get that done. So that is essentially what we are going to be dealing with in this particular course. And what we are going to handle in this whole thing, if you look at it as a summary of whatever we discussed over here, you're essentially saying that the AE352, which is your nonlinear mechanics of composite structures, is essentially the ability to perceive the profound, real, stationary principle, which is potently unifying order. So in other words, you have a real stationary principle which is potently unifying order, and that is what you are able to perceive, and that is the reality. So on the other hand, what you're doing this, where you're doing this, even amidst our manifest model or modeled motion, you can say, kinetically diversifying chaos. So this I'm saying potently and kinetically to include the preposition of over here as well. So earlier we had seen that it's real stationary principle and unifying order, and we are also seeing that what others are looking at it, if they're not trained engineers, is the modeled motion in diversifying chaos, whereas what we are doing by bringing in that preposition of is that as a good trained engineer, as a capable trained engineer, we are able to perceive the profound real stationary principle potently unifying order, whereas the untrained eye or a layman typically looks at this as a manifested modeled motion kinetically diversifying chaos. That is essential for us as engineers to do that, but we always come back from that, drawing that inferences and therefore takeaways for whatever we have done as part of that to bring back knowledge to the real system. So that is essentially this whole process of nonlinear mechanics of composite structures. And in accomplishing this, what we are trying to do is that we use a certain medium. How do we accomplish this whole task? It's nice to speak all this philosophy and then leave it at that, but we are going to get our hands wet and actually do these things. So to be able to do this, we should have certain tools in place. And the tools are what distinguish an evolved human being as opposed to lesser forms of evolution. Even if you go to Charles Darwin's theories of the survival of the fittest, essentially the way we have evolved and we have got to the stage where we are, predominantly what distinguishes us from the rest of the animal kingdom or even the plant kingdom is our ability to utilize tools like this pencil or a sword or an aircraft. So these are all tools that we develop, we engineer, we create these so that we can accomplish the same things that we have been anyway doing, but we do it better, faster and cheaper. That's all that we are doing. By having an aircraft, we are going from point A to point B, which we would have anyway walked. If we had no tool, we would have walked. Just like any animal, it moves by using its limbs, right? So same way we could have done. So, but we have invented a tool which does the same thing that we do, which is walking, but does it much faster. And maybe it carries much more, many more people and has the stamina to do it for much longer distances. But birds migrate intercontinentally too with the little food that they eat. So nothing big deal. Nature has been doing it for a long period of time. So if you look at any engineering entity that we have developed, be it a computer, be it a mobile phone, or be it any of the transport vehicles or our civil engineering constructions like bridges, the houses, etc. They're all things that are there in nature, but done in a more refined way, which can be more utilitarian in nature. So whatever we could see, we tried to see better by using a microscope or a telescope to see things which are very small or very far away, respectively, right? So similarly, if you're looking at a phone, essentially what your ear could do already, but you could hear only somebody who is speaking just next door or at the most next street. But now you're able to hear somebody who is across many continents because of your mobile phone. So essentially, you have improved that ability to see or ability to hear, ability to taste, ability to smell, ability to touch, and the haptics that is associated with it, which are touch screens and so on and so forth. So essentially, whatever we could do, we are trying to do through engineering products. We are trying to do in a better, faster and cheaper way, or a more affordable way. Cheaper sounds a little degrading, but essentially what you're trying to do is to improve the economics of it and do it in a way which is affordable for a vast majority of our brethren. So that is essentially what the whole purpose of engineering is, which means that we should have certain tools. So it's nice to say that what is nonlinear mechanics of composite structures. Structures, we have summarized already that it is the ability to perceive the profound real stationary principle potently, and potently is basically to associate the potential energy associated with the proposition of unifying order. Unifying is the composite aspect and order is the structures aspect. Okay, so so essentially what you're doing is this structure is the order that you're relating with, the composite is the unifying aspect that you're dealing with, the off is the potency aspect that you're dealing with, the mechanics is the stationary principle that you're dealing with, and nonlinear is the reality that you're dealing with. So, and this is a profound thing that you're doing. It's not possible for every Tom, Dick, and Harry, right? So you have to have a certain, let's say, level of intellectual capability, which is either acquired or it's basically developed through your efforts, self-effort, self-study, etc. You develop this profoundness of the ability to perceive this. And where are you doing this? You're doing this even amidst or within because we are the one who created that model in order to make our life simpler. So our own manifested or modeled, let's say, motion, and to take care of the preposition, kinetically diversifying chaos. So once again, the chaos is associated with the structure, the way other laymen look at it. The diversification is associated with the composite, where there is diversity of fiber and matrix. The kinetically is associated with the preposition of. We are talking of the kinetic energy there, and then the motion is associated with the mechanics, and with dynamics being the superset of statics, as we said. And then the manifestation or the model is what the nonlinear aspect is, so that it's as close to the reality as possible. If you have a linear model, it's also a manifestation, it's also a model, but you may not be able to get very useful inferences for a lot of practical real life problems. So that is essentially what we are doing. So we understand what is this thing that nonlinear mechanics of composite structures is, in terms of what the laymen see and what we see as trained engineers by the end of this course. So this is what we have to develop this ability through the next 2-3 months that we have this course. We have to have this ability to a profound ability to have this kind of a perception, as opposed to the perception that is written in red font over here. And in order to do that, we have to have a certain a set of tools. As I said, tools are what distinguish a human being from any other creature on this planet, be it from the plant or the animal kingdom, from which we have evolved, and therefore we have those additional abilities which can be sharpened. We might have put it to sleep, we might have kept it latent in our animalistic life, but there is a way in which we can resurrect that and bring it to fruition. So that's essentially what we will look at in terms of the tool. So, but if we want to use those tools, we should have some motivation to do this. Why the hell should we do this whole thing? Whether it is for composite structures or for any other branch of study that you're engaging with in aerodynamics, controls, or let's say propulsion, or those of you who are non-aerospace engineering students also in this course, the civil engineering or mechanical engineering products or machinery or buildings, etc., that you come up with, what is the motivation in doing this whole thing? Can't we do it the usual way we are doing it? Yes, there is a certain lack, and we will look into those lacks, what is lacking in step-by-step process in the next class probably. But right now, if again looking at it from the overall perspective, if you look at it, there has to be a certain motivation for what we are doing. And what is that motivation that is there? for us to do whatever we want. The way everybody does it, or the animal or the plant kingdom does it, is just a subjective reality. So that is what I'm writing in red. There's a subjective reality in the sense that it varies from person to person. Subjective. Survival. See, all that the animal or the plant is trying to see is how to survive. Even in its reproduction or the way it permeates, it's trying to last beyond its death through its genetic propagation. So that's essentially what it is. And we do that too. There is a subjective survival. So what is it that distinguishes us from the animal or the plant is what we want to get into, and which is what the essence of courses like AE 352 should be, is to go from the level of just pure subjective survival to an objective knowledge. So being subjective means that varies from person to person. Objective is the truth that is ultimate, which is permanent, which is not something that I say or you say, but it is something that is universally acceptable, universally valid. So that's essentially what you're doing, which we'll write in green, just like the traffic signal, green and red. That's the kind of symbolism that I've been using. Actually, I should have put all of this in green as well. So what you're looking at is, instead of subjective, you're looking at objective. And instead of pure survival alone, we want to know about these things. So that's essentially knowledge. So we are developing a body of knowledge that not only we can use for the specific problem that I might be interested in. I want to size the flap over here and the aileron. So aileron is outboard and the flap is inboard. I want to determine out of this span of, let's say, about 10 meters that might be there, how many meters should be the aileron, how many meters should be the flap. I want to make this decision. I can solve this specific problem by using some existing body of knowledge. But if I want to create something that others as engineers can use it, probably design engineers can use it in a jiffy and come up with really optimal solutions, then I have to develop a body of knowledge. Instead of getting a specific solution for this and say that let the aileron be of the let's say 6 meters and the inboard flaps, which is only to increase the lift for takeoff and landing and a few other aspects, let that be let's say about 4 meters out of the 10 meters that we have. That is a specific solution you come across that an engineer with just a BE degree can do. But what is it that we as master's students, and eventually with a master's degree, or a PhD student eventually with a doctoral degree, what is it that additional capability that we can get is to develop that body of knowledge which is valid for a class of problems rather than a specific problem. So you're not trying to solve one particular homework or one particular exam problem, but you're trying to address a class of problems, so that whatever body of knowledge you develop from that, the takeaways can be there for many other problems also which fall under that class. And that's essentially the objective knowledge that you're talking about. So moving from subjective survival to the objective knowledge. So that is essentially your motivation for this whole thing, is essentially that. And then there has to be a particular medium in which you're employing in order to accomplish this whole thing. So that, what is that medium that you're trying to do this? So though I'm trying to tailor it and make it specific to the course that we are dealing with, this is for any 300 level course or any doctoral level course that you're taking. And you can actually look at from this perspective any other courses, even the 100 or 200 level courses that you might have done or will be doing or are doing in parallel with this. You can actually look at it from this bigger picture, and you will see elements of this are there in all of them too, but just that people are not patient enough to look at that. But once they look at that, then the pieces of the jigsaw puzzle that you have to deal with and the pieces of the jigsaw puzzle somebody else has to deal with are not kind of independent. It's just part of one big universal creation that we are essentially creating. So it's always good to see, go to the details, that is the depth, but unless you understand the breadth, you'll not be able to achieve that. So you essentially you broaden the vision and you deepen the roots. That's what a tree does, right? So a tree, the deeper the roots are, the broader its branches will be, and any bird or anything which sits on it, not only for itself, but it serves so many other creatures which come and sit or perch on the tree, they have a much broader vision. So because it has gone so high and it's gone so broad, so it can take so many more birds. So essentially what you're doing is if you try to do only one of these, then you're not so useful. You only deepen the roots, dig deeper and deeper into a particular body of study in doing research, a very, very narrow field of interest you have. It's good because you might find something very, very useful. But that is not the thing that most engineers or most scientists need to do. What most scientists or engineers need to do is, there's already so much of depth that is available because of our predecessors who have worked on many of these problems. Now can we take all of that, combine it and address reality? And that's where the broadening of the vision comes into picture. You deepen the roots and you broaden the vision, both of these simultaneously. So that means that you need to have a certain medium through which you have to do this, and the medium that everybody else utilizes is purely sensory experience, right? And we also do that. But can we take it beyond that sensory experience? Of course, sensory doesn't mean it stops with the senses. The eyes see, the inverted image falls on the retina, but then that's not enough, right? That has to be taken by the nerves to the brain, and the brain processes whatever the optic nerves delivers to it, and then sends back the information which can be utilized by our actuators, which are our hands. Or let's say a snake is coming towards it, the eye sees it, and then the legs are given a message from the brain, run away, take the body and run away farther away from the snake. So essentially that there is a sensor, which is the eye, the actuator, which is your leg or hand, and then in between, the control system that is there, your brain has processed this particular information. So essentially in this medium, you have a certain sensory experience which everybody deals with. Just because I'm not a PhD or I'm not a professor doesn't mean I'll run away from that. I'll not run away from a particular dangerous situation, right? So, or try to handle it and survive from that. So for all of that, sensory experience is required. But what is it that we, especially as a PhD, can do? What is it that extra thing that we can do? And that's essentially the intuitive existence that we are trying to approach. So we don't stop with the sensory experience that everybody else does, and we also do, but we take it one step further. Okay, I have had this sensory experience this time. Suppose a similar situation happens next time, what can I do? And if this situation happens to somebody else, what they can do, and what we as a society can do. So trying to arrive at certain objective knowledge for this can be done only through understanding existence rather than only worried about my survival. So we have to understand the existence as a whole, wherein that particular particular thing which caused the damage in that example that I gave, the snake, also becomes a part of your ecosystem. Now you look at it, the whole existence as a whole, rather than as these individuals, one is bad, one is good, and how the good escapes from the bad. This is too simplified. Might sound good for a nursery rhyme, but not for a PhD level, where you're looking at this whole ecosystem that you're trying to develop and how you address certain problems in certain aspects of the ecosystem. Let's say the engineering part of it should not adversely affect what is the economic aspect to it. So all of these are building blocks to the same ecosystem, and anything that you do should be beneficial to the whole ecosystem, and not to the jeopardy of certain parts of it. So that's essentially possible only if you have that medium of intuitive existence in addition to everybody else's sensory perception or experience. So that's as far as the medium is concerned, the motivation we have seen. Then we should have a certain process to do this. We have to have a certain process by which we can eventually go to a certain level which others have not so far. That's the whole idea of a doctoral program in particular, and research in general, whether it is R&D in the industry or R&D in academia. You're trying to do something which is kind of original or genuine, but essentially there's nothing that you can do from scratch, as I already said. But at least in terms of the incremental knowledge that you are adding, is that original? Is that something that others have not done? Am I able to contribute that for the benefit of the globe or the universe as a whole? So you should have a certain process that accomplishes that. So what is the process that we can undertake? So that process, if you look at what the untrained or a lay person typically would do, especially those with a religious bent of mind, or those who are, let's say, just learnt from things that are not genuine sources of knowledge, just by going through certain websites, let us say, written by those who are not capable enough of understanding the problem or solving it, and anybody and everybody can write, and you just do a Google search, and then you get the information, and then you act upon that. So there is a lot of assumptions that are involved. So the process that is used by most people is that they don't know something, but they want to know, or they want that knowledge to achieve something, so they just assume things. So if you don't know something, you have to find that out. That is what search and research is all about. It's beautiful words. Some of these English words are really coined in a way that what I was talking about earlier as the correlation between the meaning and the sound, or more so the word in this case. So the meaning, search and research. So it means that it already exists. It's not that you're going to find it out. That's why I say there's no such thing as an invention. So-called inventions are higher levels of discovery. So you discover certain things which are already there, which seems obvious to many people, then it's a discovery. But if you discover something that others have not seen at all, then you call it an invention. But essentially inventions are also discoveries, but the value addition of knowledge that you bring about in an invention is much more in an invention than compared to what is typically conventionally called as a discovery. But even discovery, you see that something is covered and you are uncovering that. That is why you say discover, right? So that's essentially what you're doing. Whereas the normal people who are not with that bent of mind of search, research, discovery, and so-called invention, if you don't have that, you are going to just whatever you don't know, you're going to assume. So the process that they use, is to just assume something, or those with a religious bent of mind believing So you have a set of belief systems that come up with it, and the so-called rationalists or atheists would go to what is known as thinking. That is also a very common thing that anybody can do. Okay, but all of these are basically generating your own ideas and not actually perceiving reality as it is. If you only have a keen ear, a keen eye, and observe things appropriately and get the appropriate inferences, you would understand reality as it is. But you mess it up with your own thoughts, with your own ideas, and essentially it becomes more complex than what the reality is. Many problems have much more simpler solution than what most engineers provide, primarily because of this, that they have too much of a complicated thought process, ideation, that kind of spoils the whole solution process and eventually the value of that solution. So what is it that we can do as trained doctoral aerospace engineers, especially in related to this particular course, Nonlinear Mechanics of Composite Structures, but in general? So what is it that we can do the process different from, instead of just assuming, instead of just believing, instead of just thinking? Here, what is most essential is that witnessing what is happening, and very, very keen observation skill. That is the very first step of, leave alone a PhD, even a science student who is just exposed to science in, let's say, middle school. The most important thing that they have to do is to observe, and observe reality apart from what they see in the lab experiments. Observe what is happening all around them, and that's essentially in a non-intrusive fashion, because otherwise that subjectivity comes in. What we are interested in, remember, is the objective aspect, not the subjective aspect. We are interested more in the objective aspect, and in order to be able to do that, we have to do this thing what we are supposed to do as the process over here in a non-intrusive fashion. And what do we do non-intrusively? Instead of assuming, believing, thinking, ideating, etc. I can include that as well here. Instead of doing all that, what you're trying to do over here is witnessing. Because that's half the job done. I say to a lot of my students, the problem definition is half the job done. On some subjects, if you are learning, the terminology is half the job done. So if you know that, if you have observed what are the terminology they're using, it's essentially the same old physics and maths that you have learned in school. They're just using some jargon associated with their own fields, and it looks very complex and complicated, and the person who is talking looks like he's at some level much higher than you. But essentially, if you learn the terminology, the jargon, and in real processes, the actual process which is happening, so then you have learned most of it. So the process that we would like to incorporate is to bring in that observation skills, the ability to observe what is actually happening. So for example, when you are applying it to a beam-like problem, very interestingly, one of the students asked a question in a previous class, I think the end of the first class, about why we need to deal with wavelength. Why can't we deal with the actual geometric length? What is it that, why we compare the cross-sectional size of a beam with a wavelength to understand whether we can treat it as a beam or not? See, that's the kind of observation you need, because if you observe that in high frequency dynamics problem like impact, or where the forcing function is having a wavelength which is much smaller compared to the length of the beam, then you're actually dealing with a very small portion of the beam, and therefore it becomes almost of the same order of magnitude as the cross-sectional dimension, and therefore you're not able to treat it as a beam. So that keen perception, observation, witnessing, as I say, is what is essential over here. So what are you witnessing? You're witnessing, I already said, non-intrusively. So if you're non-intrusively witnessing, that means you're not letting your ideas, your thoughts, your belief systems, your assumptions to spoil that observation. So when you witness reality as it really is. You don't make a mess out of it already. Then, of course, you create that model in order for you to play around. That's a part of your game. That's the part of the trick that we have to earn money and to have jobs. But essentially, if you understand this process, your job becomes a easy peasy lemon squeezy thing. You just don't need to toil or do what most people call as hard work. It's very funny that many people think of hard work as a great asset, as something very good on their CV or resume. If you're doing hard work, you're not as good as you're only as good as a donkey. A donkey also does hard work. Why does it do hard work? Because it doesn't have the intelligence to do the work efficiently. The whole purpose of variational asymptotic method and this course AE 352 is to teach you how to do the same thing with the least effort. Can I do this same job, accomplish the same task, arrive at the same solution, which is accurate, which is asymptotically correct, but do it in a jiffy? Can I do that? Can I improve my efficiency? Not only my efficiency, but even the efficiency of the computer that I'm working on. I don't want it to do hard work either. Neither do I want to do hard work, nor my students to do hard work, nor the computer to do hard work, because hard work is a sign of the person doing the work without developing a certain level of capability, certain level of intelligence, not training the body, the mind, the intellect, and the energy system that we are made out of to do things in an efficient way. There is always a optimal way of approaching the problem. Then you don't need to toil, do hard work. You have to do smart work, and that's we deal with smart materials, smart structures. If we ourselves are not smart, what the hell smart materials we are going to work with, smart structures that we are going to deal with? So that's essentially the whole process of non-intrusively witnessing as it really is. Then only you go away from these whole baggage that we have of entanglements called assumptions, beliefs, ideas, and thoughts. So you go beyond that. You clearly observe the problem, clearly observe the terminology that is associated with it, the jargon that is associated with it, and go to the root of what it is all about, and then you try to address the whole thing in the most efficient way possible. And we're talking of most efficient way. It's not that I say it is most efficient, therefore it is efficient, or somebody else says it is efficient, therefore it is efficient. No, you have to have a mathematical guarantee that yes, it is the most efficient way of doing this. I start with something which is rigorous physics, rigorous science, but still my mathematics, state-of-the-art mathematics should be such that I accomplish this whole task in the most efficient way. While I balance the accuracy with the efficiency, I'm balancing the rigor with the engineer friendliness. So all of these that we talked about in the previous class, that is essentially coming to fruition over here. So one last thing with which I will complete today's class. So that is, we have seen the process. Next, let us. So we saw the medium. So first we saw the motivation, and then we saw the medium, then we saw the process, and finally, what is it that we are achieving? Okay, so what is the takeaway? What does it lead to? So that's essentially what we will look at over here. What does all of this lead to if we do it in this particular way? What would it lead to for the others? If they are doing all these assumptions, beliefs, thinking, subjective survival, sensory experience, modeling motion kinetically, diversifying chaos. So all these things which are their manifestations, if they are just completely entangled, embroiled in that, what it eventually leads to is just a bunch of ideas, let's say thoughts, opinions, and very funnily most papers end with what are known as conclusions. Even thesis end with conclusions. That's the most stupid thing you can do. You're saying, or let's say the most arrogant thing that we can do is to make a conclusion, which means that we are saying that it has concluded. Like in the movies, they say the end. The director decides it's the end, and so it's the end. But what happened to all the characters in the story? Well, they have a life after that, right? And the situations, how they develop, etc. There is something beyond everything. So the very act of conclusion is like sounding the death knell to something that is a continual process. So all that you, at the most, you can do is get inferences and not conclusions, and leave the body of knowledge open for further development. And that's how knowledge develops. Even great people like Newton, Einstein, and many others have been proven wrong in certain parts of their works. And that's how the body of knowledge develops. There's no hard and fast rule, okay, just because this is a great guy, his name is very popular, whatever he has done or she has done is something that we accept with a blind eye. No, everything is to question. Even if it is the kind of people that we'll be dealing with in this course, like Dewey Hodges or Victor Berdychevsky or myself or any of my students, whatever we do, we prove to a certain level at this point in time that it is better than whatever was existing earlier on. But whether it will remain so all the time, wouldn't there be something better than that? Of course there would be. So that is the room that you give for the knowledge to develop further. Therefore, don't ever make the mistake of making conclusions. Conclusions are sounding death knell to a body of knowledge, which is never possible. So what does this lead to? In our case, with this we will stop, is that instead of ideas, thoughts, opinions, and conclusions, what we are ending up with observations. That is the very first thing that we have to do. That's something it leads us to do, and we don't stop with those observations. That observation creates a certain wonder in us. So there is that awe, that surprise element, rather than taking everything as, I know this, I know that, I know that. This is a know-all kind of a thing, which is actually not true. How much ever you know about something, it's only then you realize that how much you do not know about it. So it's important to understand that our knowledge is a very, very, very small fraction of our ignorance. Our ignorance is far, far deeper and far, far broader than any of the knowledge that not only I or you, but even the smartest of the scientists or the smartest of the human beings, not currently, but throughout human history, whoever has walked on, there is much, much more to know in terms of knowledge than what has been tapped into. But even the little that we tap into, there is so much that we can do with. That is the beauty of this whole thing, that just by getting a glimpse of something, we can achieve so much. And that's possible if and only if these two things are built upon. That is, whatever we do, it has to lead to a certain level of observation and certain wonder about things that we have not known so far, rather than assume everything to be known. Which means that what are the milestones that we get into are not conclusions. The milestones that we accomplish are not destinations. They are instead inferences. So the inferences that we have eventually are supposed to lead to the so-called truth. But the so-called truth is also not one specific thing. It's levels of truth. It's like a ladder. You keep going up the rungs of the ladder. It's an ever-increasing ladder. So you go closer and closer to the truth, but you never are at the truth really. So in that sense, that is what it is leading to. So it's not the truth, but levels of truth that were better than whatever is the body of knowledge that has already been published or patented, or that the existing scientists or the past scientists had or engineers had. You are trying to take it to the next level, to have something that is even more closer to realities. That is the truth that we are trying to achieve. So essentially what we are dealing with here is asymptotically we are approaching what is called as the wisdom or the truth. These are things that for which exact solution is not possible, and therefore we are asymptotically approaching the truth, asymptotically approaching the wisdom, so that each step that we take, each higher order approximation that we take, makes things more beneficial, more utilitarian, not only for us but for the entire society. Thank you very much. With this, we conclude today's class. Again, as always, I'd be happy to answer questions, if any, for those who would want to stay beyond the class.
Excuse me, sir.
Yes, please. Yeah.
Sir, thank you very much for an insightful lecture. And I just want to ask two questions.
Yeah.
Sir, one is related to superposition principle. So, as I understand, that if a structure, let's say a beam, it is subjected to movement, distributed movement, and also a load. And my intention is to find out the deflection at a point in a beam. So, if I use the superposition principle, I can first find the deflection due to the moment, and then add it with the deflection caused by the effect of load. But what's there other than this, what I just said, to superposition principle?
What is there other than this? Yeah, very good. So whatever you said regarding concentrated load, which is occurring on this aircraft, let us say the simple example would be the aircraft engine that is there over here, which is having its self weight, and the thrust that the engine is generating are concentrated forces which are acting at that particular location where the engine is attached to the wing, and the lift distribution is basically a distributed force that is there, which is causing bending moments, and this transverse load is also causing bending moments, and they are in opposite directions, and one is relieving the other. So if the behavior of this was linear, let's say it was a very thick structure, and the materials that you're using are so strong that the stress levels are very far away from the nonlinear limits of that particular material, leave alone the yield and the ultimate, but even the nonlinear limits of that material is not reached, then basically the material is behaving linearly because it's a very thick structure. The geometric linearity is also there. It's a short stubby beam like you see in the Beluga over here. Very funny aircraft, but very useful to carry different aircraft parts. But here you have a situation where you have a short stubby beam which is having materials which are capable of handling much more stress and strain than what is applied to them. Then in such a situation, they're all operating in both geometric linearity and material linearity, and what you said is absolutely right. I can deal with the engine load, both thrust and weight, separately as one separate problem, and then I deal with the lift distribution as another separate problem. Then of course there are many other things like drag distribution, the pitching moment distribution, etc. Each one of them I deal with separately, and then I add up all of these to get the total, the stress due to the engine, both thrust and weight, and due to the lift, and due to the drag, due to the pitching moment. If I add the stresses due to each one of them in a particular direction, at a particular cross section, at a particular point, then I can just add up all of those individual calculations and then tell this is the total stress that is there in that particular direction on that particular surface. That would be good enough. But when you have, let us say, a structure like this, which is much thinner, in the case of this particular aircraft, which is the extra wide body A350 XWB. So here you have a very thin structure, let us say, and which means the geometric nonlinearities become important. In other words, the strain displacement relationships are nonlinear. We'll see all of these in more detail as we go through the course, but just to answer your question, or let's say the materials used are such that they're stretched to their limits in terms of their behavior, and they've slowly gotten into the nonlinear material behavior. If either one of these happens, either the strain displacement is nonlinear or the stress strain is nonlinear, then you cannot just add up the stresses the way, or the strains the way, or the displacements the way we did it in this particular problem, a short stubby beam with materials which were much stronger. I'm not actually talking about the Beluga and 350 over here, because the design would be such that even for the Beluga you would try to make it as efficient as possible in flight, so it consumes lesser fuel to take the aircraft parts from where it is manufactured to where it is to be assembled. But nonetheless, I'm just using these two as examples of one situation where let's say linearity is valid, and the other situation where the linearity is not valid. So you have to go for a nonlinear problem. So you're asking, what is the principle of superposition there? So the principle of superposition, your example is absolutely right, that now I cannot add at a given point, let's say on the root, on the top surface, let's say at the leading edge, if I want to find the stress, I cannot find the stress by finding the stress due to the engine weight and due to the lift and the drag and the moment separately and then add them up. I have to take all of them into account simultaneously and get to them. So this is only one example of what is the situation where the principle of superposition is not valid, or the principle of superposition is valid, where you are considering the loads individually and then arriving at let's say the displacement, deformation or stress or strain levels separately, and then you are adding up. In one case it is valid, and the case it is not valid. But this is something which is a much more fundamental mathematical principle, the principle of superposition, to distinguish anything that is linear from anything that is non-linear. So if you have an algebraic equation, let us say, let me just share my screen. Are you able to see my blackboard again?
So it's in the process for me.
You should be able to see it now?
Yes, now I'm able to see it.
Yeah. So what you're trying to see over here is, let's say you have a certain equation. Let us say y is equal to mx, right? So let's say there are 2 points which are falling on this curve, which are, let's say, x1 comma y1 and x2 comma y2. Right? So then you see that y1 therefore should be equal to m times, where m is a constant. Okay, so m times x1, and your y2 is equal to m times x2, and therefore you can think of these as the loads that you're applying, and this is the, let's say, the displacement that you're getting or the stress that you're getting at any particular point, and then you see this relationship is valid. When I change the load from x1 to x2, I'm getting the displacement or stress change to y1 and y2, and now I apply both of them together, like what you are saying, that the concentrated force and the distributed force are applied simultaneously. So then I can just add them up and then say that I can get y1 plus y2 as just m times x1 plus x2. It is valid, right? So this is essentially the principle of superposition that you're talking about over here. But the same thing is valid in the case of the let's say if even if you had, as I said in an example in the very first class where we were all talking about proportionality, there's no proportionality involved over there. You're basically looking at plus C over there. It's not that you would have both and say it is plus 2C over here, because in this case you would have had a plus C, in this case you would have had a plus C, and if I add these two equations I'm going to get 2C, which is not on the same line as in the previous case. Now the intercept is going to be at a different location. So in other words, if I draw the y versus x curve, in one case it was like this, in the other case it's the same slope, but it is at double the intercept. So this is at C and this is at 2C. In both cases, the slope being m. So that's essentially what you're looking at. But what the principle of superposition does is that it's for the difference that you're seeing, that if you look at the y1 minus y2, you are essentially getting at x1 minus x2 because the c's are going to be cancelled. So without that constant that is there because of the intercept, you are able to handle that. So that's why the principle of superposition is so important, much more than the proportionality factor. But this extends to a lot of things that we do, because I talked about the geometric nonlinearity being a nonlinearity between strain and displacement, and that is, as you know, let's say gamma xx, normal strain in the x direction in the linear case is just going to be given by dou u by dou x. Right. So, so if you apply for the concentrated load case, then your gamma xx only due to the concentrated load is going to be related as dou uc by dou x, and due to the distributed load, like the on the beam you talked about a distributed force, in the wing I talked about a lift distribution. In either case, the gamma xx that is there for the distributed case d is going to be dou ud by dou x, and then I can get the total actual gamma xx at that any particular point or as a field as just the sum of these two, and then write it as dou uc plus ud by dou x. Now this is also a principle of superposition. So principle of superposition or the linearity, nonlinearity difference is something that can be explained from the specific example of structural mechanics that you took, from an aircraft kind of an explanation that I gave, an algebraic equation that we saw over here, or a differential equation that we saw over here. In all of these cases, you are having that distinction between a linear problem and a nonlinear problem. Here, you could have more terms which can make it, let's say the green strain that you're talking about, you'd have, say, quadratic terms there. So when you have either u's or their derivatives, whichever order, but not power 1, but other than power 1, you end up with a nonlinear strain displacement relationship there. And then you cannot anymore add these quantities in this way to get apply the principle of superposition. So principle of superposition, as the name itself suggests, is position and superposition. You position certain parts and then you superimpose on that other parts to the whole problem, and then you get the solution also as the superimposition of the various solutions to the various problems to get the overall solution to the overall problem. So that is essentially what the principle of superposition is. It has a much broader meaning mathematically and scientifically than these specific examples like the structural mechanics example that you gave or the aircraft example that I gave. Does that answer your question?
Yeah. Thank you very much.
Okay, you're welcome.
Yeah, you definitely have added new contribution to my definition of superposition principles.
Thank you. Anybody else? Any questions? Okay, thank you then.
Hello, sir.
Yes, yeah.
Sir, my question is a little bit about logistics. Like, what will be the marking scheme of this?
Yeah, I will be talking about it in the next class. Just that I wanted to give the bigger picture before I go into the markings. But just to give you a preview to that, you will have a final exam which is of 50%, and then you will have the assignments and midterm exam. I've still not decided between the two. One of them will be about 30%, the other might be 20%. So the assignments will be kind of spread through the course, but you may not have too many assignments. So essentially it is half before the finals and half for the finals.
Okay, thank you.
Welcome. Okay, thank you very much.
मृत्युञ्जयमन्त्राः
त्र्यम्बकं यजामहे सुगन्धिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् ये ते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा